Welcome to the Deep Dive, where we get into the core insights from, well, the absolute cutting edge of research.
Glad to be here.
So today we're tackling something really interesting in machine learning, specifically for robotics. If you're following this space, you know how tough it is getting robots to learn complex skills.
Oh, absolutely. It's a huge bottleneck.
Well, I've got a paper here that suggests a maybe surprisingly data-lean way forward. It's called NIL, No Data Imitation Learning, by leveraging pre-trained video diffusion models.
NIL, yeah, no data imitation learning.
The really exciting bit, training robots using purely AI-generated video as the expert. This could potentially just sidestep all the usual headaches with collecting real-world data.
That's exactly the hook. I mean, for years, we've been stuck with either, painstaking reward engineering in RL.
Right, defining those rewards perfectly is just hard.
It's incredibly hard and task-specific. Or the alternative was imitation learning, but that meant high-quality, often 3D expert data. Think motion capture suits, specialized rigs.
Especially for weird robots, right? Not just humanoids. Animals, custom designs.
Precisely. So this paper fundamentally asks, can we use these amazing generative AI tools, these video diffusion models, to just create the demonstrations we need?
The implications feel pretty big if it works. Different robot shapes, complex skills.
Potentially, yeah. It really tackles that data acquisition problem head on.
Okay, so the title, No Data Imitation Learning. For you following along, the big idea is a robot learns a skill by watching essentially an AI-dreamed video of that skill.
Mm-hmm.
Let's dive into the mechanics. How does this actually work? They're using these pre-trained video diffusion models.
Right, the same kind of tech that generates videos from text prompts getting scarily realistic now.
So they use these to make the reference videos. The robot, in its simulation, watches these synthetic videos and tries to copy them. Is that the gist?
That's the core loop, yeah. It happens in two main stages. First stage, generating the video itself.
Okay.
The researchers feed the diffusion model just a single starting image of the robot in the simulation.
Just one frame.
Just one initial frame, plus a text prompt describing what they want the robot to do. Something simple like, the Unitry H1 robot is walking, camera follows.
Gotcha.
And the model generates the video sequence. Now, crucially, the camera angle in that generated video matches the viewpoint the robot has in its simulation.
Ah, okay. So the robot is effectively watching a version of itself doing the task correctly.
In a way, yes. It's seeing the target action from its own perspective, synthetically generated.
Right. So step one, AI makes the training movie. Now, for you wondering how the robot goes from watching to doing, that's stage two, right? The policy learning bit.
Exactly.
How do they connect seeing video to actually, moving the joints?
Well, this is where the clever reward function comes in. This is what guides the robot's learning. It works by constantly comparing the AI-generated expert video with a video rendered from the robot's own actions in the simulation.
Okay, comparing the target video with what the robot is actually trying to do.
Precisely. And this reward signal has three main ingredients, essentially.
All right, break it down for us. What's the first piece?
So the first is called video similarity. They use another pre-trained model here, a video vision transformer, specifically Timesformer, which is trained on tons of videos of human actions.
Okay, so it understands movement in video.
Right. It looks at both the generated video and the robot's simulated video and kind of boils each one down to a mathematical signature and embedding in this abstract feature space.
A signature that captures the action.
Exactly. And the reward is basically how close those two signatures are. The key thing here is it captures the flow of movement over time, the spatiotemporal dynamics, not just static poses.
Makes sense. So it's looking at the overall dance, not just the steps. What's component number two?
The second part focuses more on the frame-by-frame picture, image-based similarity using intersection over union, or IOU.
IOU, right. Overlap.
Yeah. Here they segment out the robot's body in both videos. They use a model called SAM for the generated video, and in the simulation, they know exactly where the robot is anyway.
So they get masks for the robot's shape in both videos.
Exactly. And the IOU measures how much those masks overlap in each frame. This gives a pixel-level score, like, is the robot's arm in the right place now? It provides finer-grained feedback on posture and form.
Okay, so video similarity for the overall motion, IOU for the pose in each frame. What's the last piece? Need to make sure it's, physically possible.
That's where regularization comes in. These are like penalty terms added to the reward.
Royalties for doing unrealistic things.
Pretty much. Things like using too much force in the joints, making super jerky movements, so big changes between actions or joints moving too fast. And for legged robots, penalties for, say, feet sliding around unnaturally or the torso being unstable. These regularizers are super important because just copying the video might lead to impossible or just really awkward, inefficient movements.
Right, physics still applies. You can't just teleport a limb because the video looks like it.
Exactly. So the robot learns by maximizing this combined reward, match the video's flow, match the pose frame by frame, and obey the laws of physics, basically.
And this whole reward signal guides the learning process using what standard reinforcement learning.
Yeah, a modern off-policy actor-critic RL method.
Yeah.
And interestingly, for those, deep in the imitation learning weeds, they deliberately avoided adversarial methods like jail.
Why is that? Jail can be unstable?
It can be, yeah. Training can be tricky. NIL directly maximizes this imitation reward, which they found leads to more stable and reliable learning. They also have a neat trick for handling different frame rates between the generated video and the simulation's control loop.
Okay, so let's recap the big advantages here. Why should you, our listener, following robot learning, really pay attention to NIL?
Well, the headline advantage is right there in the name.
Yeah.
Autonomous expert data generation. No more tedious, expensive data collection.
Huge.
Yeah, it potentially generalizes to new robots, new tasks, without needing pre-existing demos. Imagine training a robot shaped like nothing we've seen before. How would you even collect demo data? NIL just generates it.
Solve that problem.
And the other big plus seems to be the stability and effectiveness of this reward structure. The combo of video and image similarity plus the physics regularization seems to provide really good guidance.
And they show that this works in practice, right? The paper has experimented.
Oh, yeah, absolutely. They didn't just propose it, they tested it. They got various robots, walking humanoids like the Unitry H1, Talos G1, and also the quadruped Unitry A1.
So different types of locomotion.
And they did ablation studies, too, taking out parts of the reward function to see what happens.
What did they find?
Predictably, you need all three pieces, the video similarity, the IOU, and the regularization to get really good natural-looking movement. Take one away and performance drops, or the movement looks off.
Makes sense. And they tried different AI video models, too.
Yes, that's a really key point for where this could go. They tested Kling, Peca, Runway Gen 3, even Sora, and stable video diffusion.
What's the verdict? Did the choice of video model matter much?
It did seem to. Models like Kling, which tend to produce more visually plausible and coherent videos, generally led to better imitation learning results.
Better AI director, better robot actor?
Kind of, yeah. And even more telling, they compared different versions of Kling. As the video model improved, the quality of the learned robot gaits also improved. They became more natural.
Wow. So the takeaway for you listening is NIL gets better as the underlying video generation tech gets better.
Exactly. They're directly linked. Future progress in generative video automatically benefits this approach to robot learning.
That's a powerful synergy. Okay, the million-dollar question. How did NIL stack up against traditional imitation learning, the kind that does use real motion capture data?
Right. This is where it gets really interesting for people tracking the state of the art. They compared NIL against established baselines like AMP, GIFO, DRAIL, trained on mocap data adapted for the robots.
And the results?
In several tests, NIL performed competitively and sometimes even better than these methods trained on real-world data.
Without any real-world data itself.
Without a single frame. That's the kicker. It really suggests a potential paradigm shift. Think about it. We've always assumed you need real examples. This paper basically flips the script. It says AI's imagination, visualized through video, can be a good enough teacher.
That's a fundamental shift in thinking.
It really is.
So wrapping up the main analysis for you, NIL lets robots learn movement by watching AI-generated videos, rivals traditional methods without needing real data, and stands to improve as video generation improves. Huge potential to cut data needs and broaden robot skills.
Absolutely. A very significant step. And the researchers point towards using it for pre-training, maybe then fine-tuning with a little real data, or tackling harder tasks like manipulation. Lots of potential next steps.
Truly fascinating stuff. Okay, that brings us nicely to our novel notions segment. This is where we brainstorm a bit, look beyond the paper itself. Given this idea of no data imitation, what kind of future research could this spark? Where might this lead?
Well, building on this, one direction I find intriguing is something like closed-loop NIL with environment feedback.
closed loop, so not just watching a fixed movie.
Exactly. Right now, NIL is mostly open-loop imitation of a pre-generated video. But what if the robot's actions in the simulation could feed back and influence the video generation itself almost in real time?
Okay. How would that work? Give us an example.
So imagine the robot's trying to, say, walk across rough terrain in simulation, imitating a generated video, but it stumbles.
All right, simulation physics kicks in.
Yeah, that stumble, that state information from the simulator, maybe its current pose, the fact it's off balance, could be fed back to the video diffusion model. Maybe it modifies the prompt, like robot is recovering from a stumble, or maybe it conditions the generation directly.
And the model then generates
What?
a recovery move.
Precisely. It could generate a short video snippet showing a plausible way to regain balance or adjust the path, which the robot then immediately tries to imitate.
So the expert video adapts dynamically to the learner's struggles. That's clever.
It could lead to much more robust adaptive learning, right? Especially for tasks with complex environment interactions or unexpected events. A single pre-canned video might not cover all those edge cases.
Yeah, the real world is messy.
This way, the simulator isn't just the classroom, it's also actively helping to shape the lesson plan on the fly. It becomes more of a dialogue between the learner and the generative teacher.
What's the potential real-world payoff there?
You could potentially train robots for much more dynamic, unpredictable environments without needing demonstrations of every single possible failure and recovery. Think about a robot learning to clear clutter if it encounters a weird object it struggles to grasp.
The system could generate examples of how to grasp that kind of object.
Maybe. It moves beyond just mimicking a fixed plan to learning how to react and adapt. That feels much closer to true intelligence.
That's a really cool idea. Makes the learning process much more interactive. Okay, any other novel notions sparked by NIL?
Another area, I think, is combining NIL with embodied question answering, or EQA, for task understanding.
Okay, EQA. So robots understanding language commands in their environment.
Exactly. We're seeing huge progress with large language models understanding text. Imagine linking that capability with NIL. You give the robot a high-level command like, tidy up this area.
A vague command, not step-by-step instructions.
Yes. The robot, using its sensors to see the room, could potentially use a video diffusion model conditioned on both its visual input and that language command to generate plausible video sequences of actions needed to tidy up, like picking up trash, putting objects away.
So the robot uses the command and its perception to imagine the steps involved as little video clips.
Yeah, basically generating potential sub-goals or action plans in video form. And then NIL comes in as the mechanism to actually learn the motor skills needed to execute those imagined video sequences.
Wow, okay. So it bridges language understanding directly to motor learning using AI-generated video as the intermediate step.
Precisely. It could close that big gap between abstract commands and concrete actions. Instead of programming every single possible task, the robot could generate and learn novel action sequences based on language and perception.
The real-world impact of that could be enormous.
You could see much more versatile robots, right? Household assistants you can talk to naturally, warehouse bots that adapt to new instructions on the fly. It connects language, perception, and this data-free skill learning into potentially a much more capable general-purpose robotic system.
These are seriously exciting future paths. Both ideas really leverage this core concept of using generative models to create the training data itself, pushing beyond simple imitation.
Absolutely. It shows how advances in generative AI aren't just about cool videos. They could fundamentally change how we build and train intelligent machines that interact with the physical world.
Well, this NIL paper certainly gives us a lot to think about. It feels like a cornerstone for potentially a whole new direction in robotics.
Agreed. It's not just a neat trick. It prompts a rethink of data dependency and robot learning.
Indeed. For those of you wanting to dig deeper, the link to the paper, NIL, No Data Imitation Learning by Leveraging Pre-trained Video Diffusion Models, is right there in the show notes. Definitely worth checking out.
Highly recommended.
Thank you so much for joining us on this deep dive. We hope you'll ponder these novel notions and what this no-data future might hold for AI and robotics.
Thanks for listening.
Until next time, keep exploring the cutting edge.